Okay, so thank you for coming. Today I will present you a review about quantum algorithm for image classification. A better name would be like quantum methods for existing algorithm for image classification, and we will see there's no a general quantum algorithm, a full quantum algorithm to classify images. So image classification is just to take an image as an input and to decide which is the class of the image. The typical example is the dogs and cats. You receive images from dogs and cats and you have an algorithm which tells you if this is a dog or this is a cat. So we will review the contents and this will be like a brief summary. So this will be our thermometer of quantumness of the algorithm. This is just measuring on the whole algorithm how many quantum parts with respect to the total structure of the algorithm. So there are two objectives to introduce quantum in the classical image classification algorithms. The first one is to try to reduce the complexity through exploiting the parallelization, and the second one is to try to improve the accuracy of the classification through entanglement. So in the first one there are two approaches so far. Try to construct a convolutional neural network which has this shape. We have an image as an input, some convolution operation that we will see how they work, and finally we have like these fully connected layers of a typical neural network which gives you an output of how probable this is a zebra or a lion or a cat. And the other approach, the core of this quantum algorithm, of this quantum approach, is the implementation of the quantum random access memory. We will see later, we will analyze the complexity of this algorithm, and the quantumness of this approach is just half part is quantum and the other is classical. Then we have the k-nearest neighbors algorithm, which just we have some different classes, different data points which are labeled in different classes. We have here 3 different classes, and we receive an input point which is this black point, and just computing the distance or the similarity with respect to its k nearest neighbors. In this case I chose k equal to 3. You decide to which class it belongs. So in this case the core of this algorithm is the Dark-Hoyer algorithm. Later we will explain what this algorithm does. And the quantumness, in this case, the implementation is almost fully quantum. There's a small classical part that we will see later. And now, for improving accuracy through entanglement, we have some hybrid neural network approaches. We will see different works which uses this kind of neural networks. And I have an image, I have a convolutional neural network here and a neural network here, which is just, this is the convolutional neural network and this is the neural network. And in between, I introduce a quantum layer. So we will see where we can introduce this quantum layer, how does it work, and if this actually can improve the accuracy of the classification. The core of this algorithm is just to use different quantum circuits with some entanglement. They use different ansatz, and the quantumness of this approach is just the main part is classical, and I only introduce a quantum layer. So basically this is mostly a classical algorithm trying to introduce some new features through entanglement. So we will start with the convolutional neural network approach. This is like the main paper of the whole topic of quantum image classification, the most relevant one with more citations, and it was the most important so far. Basically, I repeat, here we have a convolutional neural network. And what is a convolutional neural network? A convolutional neural network is just a neural network which makes convolution operations. A convolution operation is just, we have here an image. The resolution of this projector is not as I expected, but here we have an image. Here we have some numbers. For each pixel I have some number associated, and here I have a filter or a kernel. So what I do is I just project the kernel to the image, and I multiply this element by this element of the kernel. I do this for this, in this case, 9 pixels, and I sum up all the values, obtaining a future map here. So what I do is I take this kernel of this filter and I pass it through all the image, generating this future map with these different values. So I multiply element by element, and then I sum up all the filters. This is a convolution operation. So the classical approach is that if I have an input image, I only flat the image in some way, and I apply this kind of neural network, and I retrieve what will be the result of the classification. Well, it's proven, and it has been shown that using this kind of convolution operation, you are able to extract or to maintain the spatial correlations between pixels, and the classification is much better than only using this kind of neural networks. So this convolutional operation enhances the classification accuracy. You can have a lot of different filters. This is only one filter. You can have a lot of them, each filter extracting one feature of the image. For example, one can extract the shapes, one other the textures, other something about the color. So you can have an arbitrary number of filters. So in a typical neural network like this one, these weights are learned. So when you train your neural network, this is what is being updated, these weights between the connection of the neurons. And when you train a convolutional neural network, what is trained is just the weights of the filters. So a filter is just a matrix with some parameters, and these parameters are optimized in some way, reducing a cost function, and this is what is updated when you are training the neural network. So, okay, this is the
cost function. What are you minimizing?
Yeah, you minimize the cost function, and then
what do you want to minimize? Because in a neural network, it's clear what you want to minimize.
Yes.
You want to optimize the classification, but here is the convolutional part, so you are not updating this. How do you?
No, in the whole training, you update these weights and these weights at the same time. Yeah, it's not until this part and then you run this part, so it's all together. So now I will present like the quantum algorithm that they construct to perform this operation. So I want to have an input image, which is just a matrix. I want a filter. I want to multiply element by element, and I want to sum up all these elements. So this is done with this horrible quantum algorithm, but let's analyze part by part and only keeping like the main ideas. So we start with an input, which will be a 2 to the n times 2 to the n ray image, which is actually fitting perfectly with the number of qubits. If the image is not of this size, there are some ways to adapt the size of the image. And basically we start with this part, which is just where we find the first assumption here. The assumption is that we are able to use a QRAM, which is able to prepare this quantum state. This quantum state is quite simple. Here we have the position of the pixel, like the coordinates of the pixel, the x coordinate and the y coordinate, and here we have entangled with this position, it's the value of the pixel. So, for example, I measure this register and I find the 0, 1, here I have the value of the pixel, which is in the position 0, 1. So, they assume that they are able to find a QRAM which is able to prepare this quantum state, which later we will discuss that it's not a small assumption. So here we have the normalized value of each pixel, and it's entangled with the position. So once we have prepared the image, we pass through this unitary operation, which is just encoding the values of the filter or the kernel. So again, we assume that we have another QRAM. It's kind of magic that encodes in the position and in the associated with each pixel the value of the kernel in this point. So I have this position which is telling me this register. I have the value of the pixel here, which is stored here, and now I have associated the number which I want to multiply with. And this multiplication is doing with this next operation, which is the multiplier. And what I want to do now is to make all this multiplication element-wise multiplication. This is done. Here we have the second assumption, which will be summarized at the end of this algorithm. And what we have here, we had the value of the kernel, and now I have the multiplication between the value of the kernel here and the value of the pixel in this point. So okay, so far we have made like all the multiplication. Now I want to sum up all these weights in order to retrieve this value. So this is done using this whole part. They present this part is quite explicitly in the paper. All it can be followed mathematically. All the operations are explicitly presented. Not these operations here, but at least this one are presented. And basically, what we want to do is to sum up all these elements, and with these quantum gates, you are able to retrieve the values of the addition of the action of the kernel once we have multiplied the kernel by the value of the pixels. Okay, so in this way, we are trying to exploit the quantum parallelization because we are inputting all the positions of the image, and we are in some way, intuitive way, in order that you are able to understand what are we doing, is that we are like doing all these multiplications at the same time. So this, as big detail, that these values are stored in a phase. So these weights here, these final weights are encoded in phases. So this is why we now have this quantum phase estimation in order to retrieve these values. Obviously, this has associated a precision. And depending on the precision that you want, you need more qubits. And finally, in order to introduce some nonlinearities, because classically the classical algorithms have some nonlinear parts in order to obtain better results in order to classify the images in a better way. So this is done by this unitary operation, which is again using this second assumption. So let's see this. Once we have done this, we can tell that we have completed this convolution operation. We have just multiplied each filter by the image, and we have retrieved the future map, the output future map. Then we have in some way to decide to assign the class to the image. This is the convolutional layer which performs the convolution operation. And now, when we have extracted the features of the image, we are at this point, and we want to implement this kind of neural network to retrieve the possible outputs. So what they do is to present a binary classification. So they explain how to do only for binary classification, cat dogs, and they present this quantum algorithm, which is quite similar to the beginning of the other one. And now notice that instead of here encoding the weights of the filter, what we have here is the weights of the neural network. So with this ancillary qubit, if you finally measure this qubit, what you have is that you are multiplying all this vector, which is encoding the information of the application of the filters, with the weights, which is what is done in a regular neural network. And if here you apply some threshold, for example, if I measure this qubit and I obtain a probability bigger than 0.6, this is a zebra, and if not, this is a lion. So deciding some threshold here, you have a binary classificator. If you want to extend it to more classes, for example, for 4 kinds of animals, you only need 4 binary classifications. This is how you generalize binary classifiers to general classifiers. So what they have done is that this is a quantum classical, this is an hybrid algorithm. This is why I presented you the thermometer. All this part that I have presented is quantum, but you are evolving your state in a quantum computer through this algorithm. But once you have evolved it and you retrieve the results, you perform the optimization, you obtain the results, and you perform the optimization in a classical computer, just as an hybrid model, a parameterized quantum circuit. So the results that they obtain is that the classification accuracy with all these monster algorithm is that using checking two data sets, they obtain results which are close to existing classical algorithms in these same data sets. So, okay, this is nice. We are obtaining the same accuracy, and the goal of this part is to in some way reduce the complexity. Okay, so far we have made two big assumptions. The first one is that we are able to implement the quantum random access memory, which is not trivial. The construction of this is not specified in the paper. This is the complexity of implementing this kind of unitary. This is just telling me that I'm able to encode here the labels and here the information associated to these labels. As before, here I had the positions and here the value of the pixel associated to this position. And we have made also this assumption is that we are able to, in this, with precision epsilon, we are able to implement these kind of transformations. Okay, they claim, don't kill me, this is not my result, this is what the paper claimed. They claim an exponential acceleration, in theory, their justification is that the ability to prepare a quantum random access memory versus the exponential number of operations that you need classically to do the same, this allows them to assert that they have an exponential acceleration in this algorithm. They obviously are exploiting quantum parallelization. When we prepare the quantum states, we are preparing a superposition and we are performing the multiplications in parallel. But yeah, for me, it's quite a too big a statement to say that we have exponential acceleration only being able to prepare a quantum random access memory. But yeah, just to tell, this is like the most relevant paper in this field, and this is making these kind of assumptions and this kind of assertions. So just you to know that the field is still quite not very mature. So
but this is just the first step of development. The rest of the algorithm, the algebraic part of some.
Yes, of course. Yeah, but they don't study this part, the complexity of this part.
Study the part that
yes. Yeah, and this is the most relevant paper in the.
Could you mention if it's possible to improve the resistance of these neural networks to black box attacks?
To the resistance, what do you mean? The robustness?
Yeah, against black box attacks.
No, they don't study this kind of, no.
And any kind of input transformation?
No, they don't study any kind of robustness in this paper. And this is, as I told you, the most, with more citations and the most relevant. Because it was like the first time that they wanted to implement brute forcefully a classical algorithm into a quantum computer. So this is why this is so important. But as you see, there are a lot of assumptions here that are not explicitly explained in the paper. So now we go to this second approach.
How many qubits do you need?
How many qubits do you need? So here
For an bit.
for an bit, o sea, n bits image. Well, here the number of qubits is log of the size of the image, because here you have the value of the pixel. Here you have n qubits if the image is 2 to the n to 2 to the n. And here all these registers depend on the accuracy that you want. For example, when you perform the quantum phase estimation and when you perform these kind of unitary transformations, which are done with this second assumption. So with this accuracy. So the resources are quite huge. As soon as you try to do with a considerable big image with enough accuracy. So yes. Yeah, this in the conclusions I will mention this need of resources. So now this second approach, which I found more, the paper is more explicit. They they don't make any assumption, they explain how to perform each step. So I repeat what this is based on the k-nearest neighbor algorithm. So imagine that we have, this is a supervised machine learning problem. We have images, here we have points, which are labeled. So I have some images, and I know if this is a lion, or this is a cat, or this is a dog. So imagine that instead of being points, these are images. Each image of the training set is with the label. So now I receive an image which I don't know which class it belongs, which will be this black point, and I measure the similarity with all the points. Then here we don't have any learning process. We don't have to train anything. We only have the images labeled, and we only have to compute the distance with respect to each image, or the similarity with each image. What is the problem? That every time that I want to make a classification, I need to do that. So I have an input point, I need to compute the similarity, and I need to search the images that are closer. So in order, if you have a few images that you want to classify, this is worth it because you don't need to train any neural network, but as soon as you need to classify a huge amount of images, it's worth it to have a trained neural network in such a way that you only input the image and it retrieves you the possible output. But as you can see, the similarity computing, so computing how similar is one point to other point, how similar are two images, is just the inner product. In this case, is the distance, its complexity is of the order of the number of training points. So here we are considering m training points, that each one of these are training points. So this is linear with the number of training points, and the searching process has this complexity. So what they try to do is they try to reduce this complexity and keeping the same accuracy results. Okay, so the algorithm, this is much simpler to understand. We start with m training images, which are just the color points, and the test image, which is the black point. Then we are going to separate between the classical steps and the quantum steps. We start extracting the features of the image in some way. I will explain how, like the value of the pixels, or the brightness of the image, or the extracting in some way the features. I will explain how do they do that. Then we have a future vector which contains these features, and we prepare a quantum state encoding in amplitudes these features extracted from the image. When we have we have this future quantum state, and we are able to compute the distance between this test image and this the superposition of the quantum superposition state of all the training images. When we have computed the distance between these vectors, what we have is a quantum state which is encoding the distances, and we can make the search of the k minimum distances. When we make this searching, what we have is a quantum state which is encoding the k minimum distances. What we have to do then is to measure, and in this way we are retrieving the indexes of the images. So each image has a label. This is the first image, the second one, the third one, and here we are retrieving like the labels of the images. So the more similar images are the first one and the second one. So we are retrieving these k values and deciding which is the majority voting. It is said if I have k equal to 3, if I have 2 which are telling me that are dogs and 1 telling me that are cats, we decide that the image is a dog. So I assign a class in this way. So this is the classical part, like extracting the features and then deciding which class we assign, and this is all doing in a quantum way. So let's go step by step. The pre-processing of the image. Now we are assuming just a red, green, blue image instead of a gray image. We extract the features of the image. Here these coefficients are containing the color information, and these ones are containing the textual information. So we can form this vector here. this J, I have a future vector for each image of the training set. And then I perform the quantum state preparation. So I have in this alpha quantum state, we have encoded the test image, and this beta is the superposition of all the training images. Okay? So the image, once we have obtained this vector, is encoded in quantum states. The test image is just a simple image, but this is a superposition of all the training images. So we now compute the distances. We use the swaps test and the quantum amplitude amplification. This is explicitly computed in the paper, but the computation is a little bit long. But the important here is that what we retrieve after doing some algebra is that we obtain a quantum state, which is a superposition between all the images which contain. So here we have the distance between the test image and the J image of the training set. So
what is the distance?
the distance is just the inner product between the states, the fidelity. Here they use the fidelity.
The problem is that when the vector increases, the fidelity tends to 0.
No, but I know what you mean, but it's in separate registers. So, ¿cómo digo esto?
And the problem is that the vectors are normalized. And when you do a normalized vector, if you have the number of the size of the fiber speed growth, the fidelity goes to 0 in general, or they are equal or they are 0, same or common. So the fidelity is a very bad measurement when you have a very large system. So this scales badly for long.
Well, they use the fidelity, this is for sure. But in the transformation, I will look it again, because I think that they don't have this problem. I don't remember what they have, but they don't have this problem in some way. But no.
I'm drawing relative distances, right? So you need to, yeah. I mean, no.
No, tell me.
No.
But this is a doubt or just a comment? What you want to say?
Just a moment.
Okay. Yes, in some way this is like the output of a quantum random access memory, but here in this paper is they are explicitly telling how to construct this state. So here we have, if we measure the register and we obtain that J is equal to 3, what we have in this register is just the distance between the third image of the set and the test image. Okay, so this quantum state is in superposition. It have like the information between all the distances between the test image and each one of the training set. So now we have to use this quantum state to try to search the minimum distances. To do this, they use the Dur's algorithm. I know that this is the Dur-Heuer algorithm, but this is how they call it in the paper. And this algorithm only needs of the order of square root of k times m iterations to find the k minimum values of the amplitudes, which are in our case the distances. So then we perform the measurement and the majority voting, which is just classically, and assign the class which has more samples. And the classification accuracy that they obtain is, as before, we are obtaining the same accuracy that the classical algorithms. So then we can study the complexity, because if we are reducing the complexity but we are obtaining bad classification results, it doesn't have any sense. So okay, for the future extraction we have the same complexity classically that quantum in the quantum case, because we are doing it in the same way. For the similarity computation, in the classical case, remember it scales linearly with the number of training points. And for the quantum case, I have a constant term which comes from the swap test and the quantum state preparation, and this term which comes from the quantum amplitude amplification. These are just the Grover iterations. And for the searching process, in the classical case, this is the scaling, and in the quantum case, using this Dur's-Heuer algorithm, this is the complexity of searching the chi minimum distances. This is a figure that they present in the paper. It's just comparing these two dependencies in the searching process, just to visualize but basically what we have is a square speedup, like in the Grover's algorithm. Okay, so these are the two approaches to try to reduce complexity, obtaining the same accuracies that the classical counterparts. As you can see, they are not very developed. There are some problems that need to be faced before trying to address this kind of image classification, which is not an easy problem, as you have a lot of information. An image contains a lot of information, and it's quite hard to encode an image into a quantum computer. So the other line of the research with respect to image classification is trying to obtain and improve accuracy in the classification. So as I told you, I have an image, I have this convolutional neural network and this neural network. Remember the picture of the zebra picture, this kind of network, and in some point I introduce a quantum layer. Obviously, the complexity here is worse than in the classical case, because in the classical case you have this, and you don't have this. So what we want to do in some way is to try to obtain better results, not to obtain the results faster, obviously. Okay, so there are two approaches. Try to introduce the quantum layer in the convolutional neural network. So we have the convolutional neural network, and we introduce the quantum layer here in between. The results in this line, there are some papers studying this. Here I have put the two with more representation, basically. And the results are that using this approach, you obtain the same results that you will obtain classically introducing random nonlinearities. So introducing here a quantum layer, what is improving is that they are introducing some nonlinearities, but they can be introduced classically in an easy way. So you are not obtaining better results introducing a quantum layer in the convolutional neural network part. The second approach is, okay, the convolutional neural network is fully classical. Now I introduce the quantum layer in the fully connected layers part. Okay, and just imagine in between the fully connected layers, I have this, I have the weights. This is like a typical neural network, and these parameters, I use them as the rotation angles in a quantum circuit, as parameters in a parameterized quantum circuit. So this would be an ansatz, and in some way I'm using the outputs of this layer as parameters in the quantum circuit. I extract the expectation value of each qubit to be in the. I retrieve some information of the quantum circuit, and I use explicitly this information as this one here, as another layer of the neural network. I apply some weights and I obtain other parameters. So this is how these quantum layers are introduced in between a fully connected neural network. So using this, there are some papers that are finding that using ansatz with entanglement yields better results than classical counterparts. What's the point? That they don't know why, they don't know how to introduce it, they don't know how to measure entanglement in order to quantify how good are the results with respect to the classical counterpart. So this is like a blind search of error and trial using quantum circuits. So far it's not very developed. So to summarize and conclude, which is the state of the art of quantum image classification, is that we have studied that there are quantum counterparts of the existing quantum algorithms, like the quantum convolutional neural network approach and the K-nearest network approach. We have found that there are some parts that need to be improved, like the encoding and measurement strategies that are not explicitly explained in the papers. They are just assuming that you are able to efficiently retrieve the information of the quantum system. The parallelization in theory shows that it's possible to find a possible speed up this is in an ideal world, this is in theory, you need to have enough number of good qubits, and I found that the k-nearest neighbor approach is more promising because they don't need to implement these quantum random access memories, but it's less practical when you want to classify a huge amount of images. We have found some examples showing that entanglement could improve classification accuracy. I emphasize could improve, it's not proven, and I conclude that this is a blind search. It's not clear how to introduce the entanglement. They are only trying some different quantum circuits as an ansatz, and they are only seeing that, okay, we can obtain better results, but they don't know how to do it and how to measure it. So, like, for me, the final conclusion here is this is a quantum machine learning task, but the quantum machine learning field per se is it's not enough developed to try to address the problem of image classification. Image classification is one of the most complex problems in machine learning, and trying to implement this kind of algorithms like by brute force in a quantum computer before solving problems like encoding information, how to implement this quantum random access memory, for me it makes no sense. We have to deal with the bottlenecks of quantum machine learning in general, and once we are able to distinguish between black points and white points in a plane, once we are able to do that efficiently, we could try to classify images. But the image classification should be like the final big boss in the quantum machine learning path. So this was everything. Some doubts. You can criticize the at least that one.
So questions?
I have one question. So first, I think it's the neural network, the convolution neural network, they adapt values that are like in different amplitudes in the superposition. What's what they are adding? After doing the multiplication of
yes.
the terms of the image with the terms of the kernel, they add up those values.
No, no. They add up at the end of the whole process. So with these values, with these weights of the kernel, you obtain these values, you continue with another, for example, convolutional operation, and finally you have all the information encoded in 6 parameters. These 6 parameters go to the fully connected neural network, this final part, and just at the end, when you measure and you construct your cost function, then is when you compute the gradient of all these parameters. Yes, but not before. This is similar, more or less the same as Mikkel was asking. But this is at the end of the whole process, not only the convolutional operation. You are not stopping the algorithm in this point, just at the end.
Okay. And in the Brugge minimization algorithm, you usually need to initialize the initial state several times to be able to do it. Have they considered this part? And why do they consider a constant cost in initializing the
because
states?
They claim that they explicitly present which are the quantum gates that you have to use to the unitary that you have to use to prepare this kind of state, and they claim that the number of quantum gates is constant independently of the size of the system, and the same for the swap test. So they are like joining the complexity of the quantum state preparation and of the swap test in this constant term. But
it's independent in the size of the number of samples that you have, but not on the size of the image.
Because the size of the image, the future vector where you encode all the information, is the size of this vector is independent of the size of the image.
Okay.
Because you are just codifying all the information of the image in 80 amplitudes.
Okay.
In independently of the size of the image.
Okay, so the cost of the size of the image is only in computing the feature part.
Yes, exactly. Yes, yes. This is independently of the, but this is their approach how to encode an information in 80 amplitudes. But this could be a better way to do it. They have separated into color information and texture information. Texture 8 parameters and color 72 parameters. So they explain how to compute each value, but maybe there's a better way. But this is why they don't consider the complexity of the preparation, because it's independent of the size of the image.
So the role of entanglement is not clear.
No, it's not clear, and yeah, they don't have an intuition of what to measure. This was what we discussed about expressivity of the ansatz and how entanglement improves the expressivity, but it's not clear that this is able to really quantify the improvement on the results. So,
for example, if entanglement is in the last layer, then it's like a global measurement, so you can increase the fidelity. But besides this,
yeah, there's any theoretical work or theoretical paper trying to explain why this entanglement could improve the results. Only they can compute the entanglement capacity of these ansatz in order to quantify the entanglement that they are introducing. But there's no clear relation between entanglement capacity and accuracy. So yes, all the works are like this, with a lot of ansatz, with different rows, with different amounts of entanglement, and just retrieve the accuracy results and see how good they are. But yeah.
Because the problem is that if you introduce entanglement, it's true that you can improve the accuracy, but